Alright, let's talk about Schrodinger and Heisenberg. And when I want to talk about Heisenberg, I'm talking about this guy, not this guy. So, Heisenberg's uncertainty principle. There is a limit to how accurately you can simultaneously measure the position and momentum of an object. And I'm talking about keywords simultaneously, like at the same time. Why? Because the act of measuring the system disturbs the system. So if I have an electron and I want to see it, a photon of light has to come down, hit it, bounce off of it, and go to my eye. Yes? But while that happens, after the photon hits it, the photon has energy. And so some energy is given to this electron, and it's going to fly off. So by the time the photon reaches my eye, the electron is no longer where I thought it was. I was trying to measure. So therefore, the act of measuring actually disturbs the system. In math speak, because physicists always want to ruin things, the error in position times the error in momentum is greater than or equal to h over 4 pi. And we'll be doing some math questions with this formula later. Schrodinger. So Schrodinger thought, if I can't talk about where something is or how fast it is moving, what can we talk about? And the answer is we can talk about probabilities. Yes? We're not going to talk about where something definitely is. We're just going to talk about where there's a good, high probability that there is. Yes. So he came up with these ideas of wave equations. Yes? Wave equations describe the wave-particle duality of photons in matter. They give the probabilities of where an electron might be. And he considered matter once again as a standing wave. And it worked out really well for him. A wave equation is given the symbol phi. There's different wave equations. They all have to satisfy this equation. H phi equals E phi. H is called an operator. Whoops. And specifically here it's that Hamiltonian operator. It's basically saying take a fancy derivative of this, and when I do, I should get the same function back times some constant E. E is energy. Yes, and so if you know calculus, you would hopefully know that the basis of phi, it's got to have some sort of e to the x in it, because the derivative of e to the x is e to the x. So that's kind of like I need to get the same thing back again. After I take the derivative of this function, I need to get the function back again, and so it's got to have some sort of e to the x in it. That's as in-depth as I'm going to go with wave functions. It's more in-depth than the textbook goes, and we're just going to leave it at that. This thing will pop up in later physics courses if you carry on and take more modern physics. It's a bit of a confusing thing. When I was in school and university for many years, before they actually taught us what this is, I was wondering why I couldn't just cancel those out and let H equal E. But now as soon as they explained to me that this is an operator and it's saying take the derivative of that, then it was made more sense to me. So that's our brief little look at Heisenberg and Schrodinger.